This video is on stoichiometry, and it's an expanded version of the portion of the video from the summer boot camp that included a section on stoichiometry. So stoichiometry is a big, long word. It more or less for me means the ratios in which things combine in chemical reactions. It literally means the mole to mole ratios in which things combine, but we use it in a broader sense to also include mass relationships. So stoichiometry is generally used to work out mass relationships in chemical reactions, and we'll see examples of this a little bit later on. If you're given one piece of information, which would typically be the mass of one of your reactants or the number of moles of one of your reactants, then you can find out the amount of other reactants that are necessary to react with that initial reactant, or you can find out the amounts of product formed, again, either in terms of moles or in terms of mass. And so to do this, you're going to need a balanced equation, because at the heart of any stoichiometry problem is going to be a moles of substance A to moles of substance B conversion. But you're usually also going to need molar masses, because most often you're going to be converting grams of one component of the reaction into grams of another component of the reaction. So let's just think about an example here. And let's say what stoichiometry is not. So here is a balanced equation for the combustion of methane. One molecule of methane plus 2 molecules of oxygen give you 1 molecule of carbon dioxide plus two molecules of water. Now, instead of thinking about this in terms of molecules, we're going to think about this in terms of moles. And so really kind of for the rest of the course going forward, we would really read this to say 1 mole of methane reacts with 2 moles of oxygen to give 1 mole of carbon dioxide plus 2 moles of water. So let's just say, suppose I have 10 grams. I've just given as a starting quantity 10 grams of methane, CH4. Does that mean I need 20 grams of oxygen? Because after all, they react in a 1-to-2 ratio, one methane to 2 oxygen. Therefore, if I've got 10 grams of methane, does that mean I need 20 grams of oxygen? And the answer to that question is no, because methane and oxygen have different molar masses. So even though methane and oxygen are reacting in a 1-to-2 ratio in terms of moles, they don't have the same molar mass. So we can't simply say that if I've got 10 grams of one, I need twice as many grams of the other. Conversely, can we ask the question, okay, suppose I've got 10 grams of methane. Do I just use the ratio of their molar masses to find out how much O2 I need? In other words, do I just take the methane and multiply by the molar mass of oxygen over the molar mass of methane? The answer to that question is also no, because now we've erred in the other direction. That is, they don't react in a 1-to-1 ratio. They react in a 1-to-2 ratio. So you need to consider both the molar masses and the mole ratios. That is, we need to consider the fact that methane and oxygen are reacting in a 1-to-2 mole ratio, but then on top of that, that they also have different molar masses. So let's look at this equation again. And as I've mentioned before, at the heart of every stoichiometry question is going to be a moles to moles conversion. And so what we can say about this reaction is to use this funny little squiggly thing that kind of looks like an equal sign, but is kind of puffed up. And that literally means is stoichiometrically equivalent to. So for the purpose of this reaction, we can say that 1 mole of methane is stoichiometrically equivalent to 2 moles of oxygen, because if I have 1 mole of methane, it's going to consume 2 moles of oxygen. I can say that both of them are stoichiometrically equivalent to 1 mole of carbon dioxide, because 1 mole of methane plus 2 moles of oxygen is going to produce 1 mole of carbon dioxide. And I can say that they are all stoichiometrically equivalent to 2 moles of water, because 1 mole of methane plus 2 moles of oxygen is going to give me 1 mole of carbon dioxide plus 2 moles of water. I can also independently say that any one of these four numbers is stoichiometrically equivalent to any one of the other three remaining. So for example, I can say that 1 mole of methane is stoichiometrically equivalent to 2 moles of water, because 1 mole of methane, when it reacts completely, will produce 2 moles of water. I can say that 1 mole of carbon dioxide is stoichiometrically equivalent to 2 moles of oxygen, because 1 mole of carbon dioxide is produced by the reaction of 2 moles of oxygen. And so once I've got these stoichiometric equivalencies, I can actually convert them into conversion factors. And so, for example, there is 1 mole of methane consumed per 2 moles of oxygen consumed. Or there's 1 mole of methane consumed per 1 mole of carbon dioxide produced. Or there are 2 moles of water produced for every 2 moles of oxygen consumed. Or there is 1 mole of carbon dioxide produced for every 2 moles of water produced. Or there, and now I can also, and there are more, I'm sorry, just back up. There are more conversion factors than these. I've come up with, there are actually 12 possible conversion factors I could write. 6 different combinations of substances, plus I could write the reciprocals of these. So I could actually write 12 different conversion factors from this equation. I've written 4. The other thing that's useful to have is the molar masses of the substances. And so a mole of methane weighs 16.0 grams. A mole of carbon dioxide weighs 44.0 grams. A mole of water weighs 32.0 grams. I'm sorry, a mole of O2 gas. And a mole of water weighs 18.0 grams. And you'll notice I could write these, again, I've only written half of the conversion factors I can. In some cases, I put moles on the top and grams on the bottom. In some cases, I put moles on the bottom, grams on the top. I could write the reciprocals of these. You'll notice I've only gone to 3 sig figs with all these molar masses, and I think actually in the next problem I'm going to show I've gone out to 4 sig figs. So these are the conversion factors I can write that will help me solve a stoichiometry problem. I do want to just say one more thing before I get off this slide. These stoichiometric equivalencies are specific to this equation, to the combustion of methane. If I was doing the combustion of some other substance like propane or butane or octane or hexane or methanol or isopropanol or whatever, I would have different coefficients, and that would give me different stoichiometric equivalencies. It would no longer be the case, say, that 2 moles of oxygen gave me 2 moles of water. If I was burning something else, I would wind up with a different set of coefficients and a different set of stoichiometric equivalencies. So these ones are only specific to this reaction, whereas the molar masses are going to be general to any reaction that these substances participate in. Okay, so let's try actually doing this problem then. So the question is, and so you're going to be given quantitative information about one substance in the reaction. You're going to be asked for quantitative information about another substance in the reaction. And when I say quantitative information, I either mean moles of it that reacted, or grams of it that reacted, or moles of it that were produced, or grams of it that were produced. And what you're going to be asked for is either moles or grams of some other substance that is either consumed or produced in the reaction. And so to do this, we're going to use roadmap number 2. And whatever substance we're given information about, we're just simply going to define that substance as being substance A. It could be a reactant, it could be a product. The thing about which we are given a measurement, the quantitative information that we're given is going to, we'll just define that as substance A. Whatever substance we're being asked for information about, we will define that as substance B. And then these, depending on which way you're going, but we're always kind of going from left to right, because we're always going to define the initial thing as substance A and the final thing as substance B. We're going to use molar mass as a conversion factor. Again, over here, we would use molar mass as a conversion factor. And in the middle, we're going to use those conversion factors that we generated from the stoichiometric equivalencies, convert moles of A into moles of B. So this is roadmap 2 on your roadmap handout that I have given you? Well, okay, you're given 10 grams of methane. What mass of oxygen do you need? We decided a couple of ways not to do it earlier on. And so now let's talk about how we are going to do it. We're going to use roadmap number 2, and we're going to ask ourselves, what are we given? Since methane is the thing that we're given information about, we're going to define methane as being substance A, and we are given the mass in grams. And so we're getting on the road right here, grams of substance A. We're being asked for mass of O2. And so we're going to define O2 as substance B. And because we're being asked for mass of O2, we are going all the way over here. So we are starting all the way on the far left-hand side, and we're being asked to go all the way to the far right-hand side. And so let's just walk through this. We're given grams of substance A, which is 10 grams of methane. We're going to divide, and so it says to get to moles of substance A, we're going to divide by the molar mass. And you'll see that when we do that, you also see that I've gone out to 4 sig figs here on my molar masses. But you'll see that when we do that, grams of methane cancel, and we're left with moles of methane. Now, the next thing is to multiply by the coefficient of substance B over the coefficient of substance A from the balanced equation. And so this is one of my moles to moles conversion factors. It's got the moles of substance A in the denominator. It's got the moles of substance B, the oxygen, in the numerator. You notice now that cancels out moles of methane. And I've now converted grams of methane into moles of oxygen. And then finally, to get to grams of substance B, which is oxygen, I'm going to multiply by the molar mass of oxygen. That cancels out moles of oxygen. And finally, now you can see that I have converted grams of methane into grams of oxygen. And the answer then is going to be 39.9 grams of O2. Okay, well, we can do some more examples of this. And so let's just go through two more. Let's go through just 2 more examples. Okay, in this instance, we are being given, so we have the equation, F2, it's balanced for us. F2, fluorine, plus 2 sodium chloride gives us 2 sodium fluorides plus chlorine. And if 9.80 grams of fluorine gas are allowed to react with excess sodium chloride, that is to say, this is the limiting reactant, it's going to determine what our yield is. How many moles of sodium fluoride are formed? And so we take a look at the roadmap again, you'll notice that this is not like the previous one, a grams of A to grams of B. We're going to define fluorine as substance A because it's the thing about which we are given quantitative information, 9.80 grams. But it's not asking us actually for moles of substance B, which is going to be sodium fluoride. I'm sorry, it's not asking us for grams of substance B, which is sodium fluoride. It is asking us for moles of substance B. So we're getting on the road here at grams of A, and we're getting off here at moles of substance B. And so we are only going to do, and so therefore we're only going to do 2 conversions, grams of A to moles of A, moles of A to moles of B, and then we'll be done. So we're taking 9.8 grams of fluorine, and we are going to convert that into moles of fluorine by dividing by the molar mass, or multiplying by 1 over the molar mass. That converts grams to moles. And then to convert moles of fluorine to moles of sodium fluoride, I'm going to use the conversion factor that has moles of fluorine in the denominator. That cancels out moles of fluorine and moles of sodium fluoride in the numerator, and I'm using the coefficients from the balanced equation, 2 moles of sodium fluoride per 1 mole of fluorine, and that gives me 0.516 moles of sodium fluoride as my answer. Okay, let's try one more. We're given the reaction that 2 moles of iron plus 3 moles of sulfur gives us 1 mole of iron 3 sulfide. So if 11.13 grams of iron are allowed to react with excess sulfur, again, when we say excess sulfur, what that means is that this is, because this is in excess, it's the iron that's going to determine the yield. And so it's our limiting reactant. And so we can convert we can use iron, the amount of iron we have, to figure out how much iron 3 sulfide is formed. So now when we look at the roadmap again, we're going to define iron as substance A. We're being given grams of substance A. We're going to define iron 3 sulfide as substance B. We're being asked for grams of substance B. So in this case, we're doing the whole grams of A to grams of B conversion. So that's 3 conversions, converting grams to moles, then moles to moles, then moles to grams. Again, we'll just stress it over and over and over again. It's not a stoichiometry problem unless it has a moles to moles conversion in it. So we're converting grams of iron to moles of iron. We're converting moles of iron into moles of iron 2 sulfide using the coefficients from the balanced equation. And then we are converting moles of iron 2 sulfide into mass of iron 2 sulfide using the molar mass of iron 2 sulfide, and we get 20.72 grams of iron 2 sulfide. This is a diagram from the textbook that's essentially the equivalent of roadmap 2. It shows you converting grams to moles, moles to moles, moles to grams. I like to make my roadmap nice and long so that the grams of one thing are not near the grams of the other. I'm going to be kind of beating a dead horse here for a while, but this comes up over in my years of teaching this subject. This just keeps coming up over and over and over again. You cannot convert mass of one substance directly into mass of the other. You have to go through moles, then convert moles to moles, then convert grams, moles to grams. It's tempting to say, well, if you can convert moles to moles, why can't you convert mass to mass? And so what I'm going to do is give you what I call my my hotel room analogy. You I can't stress this enough. You cannot convert directly between grams of substance A and grams of substance B. All right, what is this? This is a picture of 2 adjoining hotel rooms. So you go off on a vacation with, say, your cousins or something like that, or extended family. You go to a hotel and you get 2 rooms that are next to each other. This is the door that opens that allows you to pass between them. So here is room A, here is room B, here's the bathroom in room A, here's the bathroom in room B. This is just a generic picture. Here's a picture actually from a resort in Cambodia. Very beautiful. You got palm trees out here on the terrace. You've got more palm trees out here on another terrace. Here's the connecting door. Here's the bathrooms. I'm pointing out the bathrooms for a reason. You will notice once again the bathrooms are right next to each other. Here is a picture of a floor plan from some resort in Jackson Hole, Wyoming. Here's room A, here's room B, here's the door to the bathroom for room A, here's the door to the bathroom, much nicer, larger, more pleasant bathroom for room B. Once again, they're right next to each other. It's tempting because these bathrooms are right next to each other to think that you might be able to go directly from one bathroom to another. Same thing here. Same thing here. But what you'll notice is there is no door between bathroom of room A and the bathroom of room B. To get from one to the other, you have to go out to the room and then go through the connecting door and then back to the bathroom of the other. And this is just an analogy for what you have to do when it comes to converting mass of one substance to mass of another in a chemical reaction. You cannot go directly from bathroom to bathroom, even though they're next to each other and have the same name. You have to come out into the room, go through the connecting door, go back into the room. Same thing in Jackson Hole. To get from this bathtub, even though it's right next to that bathtub, you got to come out into the room. You've got to go back. You've got to go into the next room. You've got to go back into the bathroom, which is exactly what you have to do if you're going to convert from grams of one thing to grams of another. You cannot go directly from one to another, even though they have the same name and they seem to be near each other in this diagram. You have to go through moles. Okay, so just a quick summary of this. You have to start with a balanced equation. You're going to start by putting the amount of material given in the problem in the first position of a train track, and you're just going to define that as substance A, and you're either going to get moles or grams. If you get grams, you're going to have to convert that to moles by dividing by molar mass. If you get moles, you can now just whether you get moles by converting from grams or you were given moles directly in the product, you're going to convert that to moles of substance B using the coefficients from the balanced equation. Okay, depending on what the question is asking for, whether it's asking you for moles of substance B or grams of substance B, you may or may not have to then convert moles of B into mass of B. That will depend on the problem. Okay, and we're going to, so in other words, you may be asked to go from moles of A to moles of B, grams of A to moles of B, moles of A to grams of B, grams of A to grams of B. Whichever of those four options you're being asked to do, there is always going to be this moles to moles conversion. It is not a stoichiometry problem if there isn't a moles to moles conversion. Okay, I think I've talked enough. Thank you very much.